In this Calculus 3 tutorial, we'll see how to evaluate the surface integral, which is also the flux, by using the divergence theorem. And this is an example from the textbook by James Stewart. First, the reason that we can use the divergence theorem is that you see that these components here, they are all very nice. We do not have anything on the bottom, right? No variables on the bottom, and no square root, radicals, natural log, things like that. They all for sure have continuous partial derivatives, so we are pretty much good to go. And this question is also set up pretty nicely so that if you do use the divergence theorem, it works much better compared to just do this directly. But anyways, what does he say? He says that our surface integral, which is the flux here, is equal to, you change that into a triple integral, and you might be thinking, oh my goodness, triple integral compared to the double integral here, how is this easier? Well, it is. Just think about sometimes the Green's theorems are easier going to be computing the line integrals, right? You have a double integral compared to a line integral. But anyways, triple integral over our solid, which is going to be bounded by this equation here, and you have the divergence of the f inside and then the v. Let's take a look at the divergence right here first. So the divergence of our vector field, remember all we have to do is, this is p, q, r. We do the partial of p with respect to x, and then partial of q with respect to y, and partial of r with respect to z. Here we go. Here, we're looking at this, differentiate the x, we get 1, so we have y. Look at this and differentiate this with respect to y. This gives us 2y. This part does not have the y, so it's a constant, it's gone. Lastly, look at this, differentiate this with respect to z, but there's no z, so it's 0. Guess what? Look, this is just 3y. How nice is that? So our integrand here is much better, but of course this is still a triple integral, so we have to know how to set up this boundary really well. Now let me just write this down right here real quick. This is going to be 3y. So now let's go ahead and figure out the bounds for this triple integral. And here it's just going to be 3y, and then we have dv. Now we have to make our selection. Which differential do we want to do first? Let's have a look. We have z is equal to 1 minus x squared. However, here we also have y plus z is equal to 2. In this situation, it will be easier if you isolate the y from here, which you get y equals 2 minus z. And in fact, I would like to start with y first. So in the y world, y is equal to 0, and you go up to 2 minus z. Next, you can imagine that after you finish this, it will be in terms of z, right? And it's very nice that we know z is equal to 0 up to this. So I will do dz, and we go from 0 to 1 minus x squared. Now lastly, it will be the numbers for x. In this case, you can just put 0 into here. Then you see that 0 is equal to 1 minus x squared. Solve this equation, you can see x is equal to plus or minus 1. So x will go from -1 to 1. And that is a triple integral that we have to evaluate, and we'll get the answer for that. And of course, we need more space, so let's go ahead, erase this. Here we go. First, I will put a 3 in the front, and then we have the integral going from -1 to 1, and then another one going from 0 to 1 minus x squared. Integrating y, we get y squared over 2, so that's 1/2 y squared, and we go from 0 to 2 minus z, and then dz dx. Now plugging, subtract, right? And the 1/2, let's put that in the front as well. And the integral, another one, and we will just have 2 minus z squared. Now, do this right here, we actually have to use a u substitution. Let this be u. So u is equal to 2 minus z. du is equal to negative dz. So be sure that when you do the power rule, you have to divide it by the negative. And we will just have 3 over 2 integral going from -1 to 1. And then you add 1 to the power divided by that. So it's going to be 1/3. But again, you have to have that negative. And the input right here stays the same. I'll just put that down like this. And then third power. Okay. And then we go from 0 to 1 minus x squared. And we have dx. Yeah, okay. Now, put this to the front, so it's going to be -1/2. And then I'm going to be plugging this into z, and that's still the same of the integral. That is going to be 2 minus, let me just, this is going to be 2 minus 1 minus x squared. Like this, right? That's the input here. So it will be 1 plus x squared, and then third power. And then plugging 0 into here is just going to be minus 2 to the third power, right? It's 2, and then minus 0, and then again, it was like this, and this is like that. So that will be 8. And we have the dx. Okay, and I'm going to expand this real quick, and we can use the binomial theorem or the Pascal's triangle. It's just 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So these are the coefficients. And we have the 1/2 in the front, negative, and that's integral -1 to 1. And expand this, perhaps I put this down first, so that will be x squared cubed, which is x to the 6, and then plus 3 times this thing squared, which is x to the 4th, and then plus, times 1, but doesn't matter, and plus 3, right, the coefficient 3, times this to the first power, and then times 1 squared, which is 3x squared, and then lastly, just plus 1. But we have a -8. So of course, together, that will give us -7. So let's just go ahead and combine them here together. Dx. And now for this right here, I've shown you guys all the computations. And right here, you can see that this is actually an even function. So you can go from 0 to 1 and then just double the result. And do whatever you need to do. It's going to be just arithmetic from here. I'll tell you guys the final answer, which I wrote it down right here earlier. You will end up with positive 184 over 35. So make sure you work that out. Yep, that's it.